right? Depending on the pace at which we move. These are the things that we would want to be able to do at the end of the topic. Define a vector, which we'll be looking at today. Represent vectors using line segments. Denote a vector with the initial point A to a final point B using the term AB. Differentiate between scalar and vector quantities. Determine when two vectors are equal. Find the sum or difference of two vectors using a triangular law. We'd also look at something called the parallelogram law of vectors, which is really just two triangles smushed together. Use vectors to model practical situation, calculate the length and direction of a given vector, multiply vectors by scalar, identify opposite vectors, and determine when two vectors are collinear, right? Once we do that, then we should be in a good position to tackle any vector questions. Now, I don't want you to be intimidated by vectors. Vector questions in the CSEC paper is some easy marks to put in the bag, right? It's just for you to grasp the concept and the understanding of vectors, right? So with that, I'm going to kick off definition of a vector. So generally, we'd assume that when we add two things, let's say we add 2 and 2, it's going to be 4. And sometimes it's not always that case, especially when we're looking at vector quantities, which is a bit different to what we are accustomed to. What we are accustomed to is something called scalar quantities. So here I have a scenario. There's this town called Amberley, right? I'm denoting it by A. Beckford, B. And Croxton, C. These are 3 villages, right? Going forward, I just call them A, B, and C. So A is 2 kilometers from B, right? And then B is 2 kilometers from C. Let me get a pen so I could write. So this A, which is one town, is 2 kilometers away from this town B. And then this town here, C, is 2 kilometers away from C, right? Now, from the diagram, we currently assume that the distance between A and C is 4, right? We can't add 2 and 2 and say, well, that distance is 4. And the reason for this is that from A to B, then from B to C, and then from A to C, they're called displacements, right? And each of them has a magnitude, there's a size. But each of them also have a particular direction in space, right? They're moving at a particular number of degrees, if we're thinking in terms of bearings, right? And vector quantities are different from scalar quantities because vector quantities have both magnitude, another word for magnitude is size, and they have a specific direction in space. They're moving in a particular direction. So generally, vectors can be represented using these line segments, right? You see in the these here, I'm getting this pen. These are the line segments we're talking about. And what they have is they have length, right? Which is we just refer to as the magnitude. And they have direction. Up on them. Oh. Right, so they have length or magnitude. Magnitude is another word for length. And they also have direction. So here, if this is our north arrow here, this line segment represents, it could be a train or a vehicle moving at 16 kilometers per hour in a westward direction, right? And we wouldn't refer to this as speed. We refer to this, if any of you guys are doing physics, as velocity, because it's movement in a particular direction, right? So velocity has both magnitude, which is the 16 kilometers per hour, but also direction. It is heading west. So it is a vector, unlike speed. So the length of the line usually represents the magnitude of the vector. So sometimes you will see we have a graph paper. So you check each unit and that represents the magnitude of the vector. And then the direction of the line now represents the direction of the vector, right? Usually there's an arrow on the line to tell you the direction it is moving in. Now, how is this different to what we are accustomed to, right? Scalar quantities, on the other hand, this is what we are accustomed working with, is only defined in one dimension, which is magnitude, size. So for example, if I have a shoelace, that's a scalar quantity because I could measure that length of a piece of shoelace or a piece of string, right, in either centimeters, in yards, in feet, in inches. Temperature is another quantity that does not have any direction. We measure it in terms of magnitude. We could say today is 36 degrees Celsius, right? Or how much ever Fahrenheit. We represent that in one dimension only. So scalar quantities is different from vector quantities because for scalar quantities, these quantities only have size or magnitude, but no direction, right? They are described with a single numerical value. These are scalar quantities. And examples of these would include things like length, right? Length is a scalar quantity because it only tells you how long or short something is. It doesn't indicate the direction. So a ruler is going to measure the length of an object, right? Or a piece of paper or piece of pencil in centimeters, right? Mass is another example of a scalar quantity. It measures the amount of matter in an object. Now we say weight, but weight is not correct, right? The correct word is mass, right? And we measure mass in terms of kilograms, grams, right? So we could say a pound of sweet potatoes or a kg of sweet potatoes is how much ever dollars. Temperature, as I mentioned before, another scalar quantity because it measures how hot or how cold an object is. And this is usually measured in degrees Celsius or degrees Fahrenheit. So water boils at 100 degrees Celsius. That's a scalar description of the temperature. It tells you how hot it is. And vector quantities, on the other hand, they have both magnitude and direction. So they are described by a numerical value, which is magnitude, and also a specified direction. A very easy example to look at is force. If any of you guys do physics, right? Force is a vector quantity because it not only tells you, right, how strong a push or pull is, that's in magnitude, it also specifies the direction of the force applied. So you could say, if you push a book to the right with a force of 10 newtons, the direction is to the right, right? It is just, the direction is just as important as the magnitude. Gravity is a natural force. Gravity is always acting downwards. It's pulling on things directly down to the earth. So we could say gravity has a I'm not telling the exact. I don't want to make it up. .81 newtons per kg, right? And that's acting downwards. That's what the force of gravity is. Velocity, as I mentioned before, that represents the speed of an object in a particular direction. It's not just speed, it's telling the direction in which it is moving. And that's measured in meters per second, right? So a car moving north at 30 meters per second has a velocity of 30 meters per second in a northern direction. Displacement, which is different from distance, measures the change in the position of an object from its initial point to the final point. That's what we talk about when we're doing vector quantities here in maths, right? So when we're talking about the relation of the tongues from each other, the A to B to C, right, is in a particular direction. So for example, I could say I walk 10 meters to the east and then 5 meters to south. So my total displacement now is 11.2 meters to the southeast, right? That's when we talk about displacement. So generally, scalar quantities have magnitude. Examples of these would include things like length, mass, and temperature, whereas vector quantities, they have both magnitude and direction. Right? Both magnitude and direction. There we go. This is what I can do. I need this down at the bottom. Right. Nothing, just in case anybody joined the room. Good. So let's see if you understand what we're talking about there. So I have five things here. The length of a piece of wire, the force needed to move or lift up its shaft, a move from the door to your chair, the speed of a galloping horse, the distance between Kingston and Montego Bay. Which of these are vector quantities? So all you need to type in the chat is if you think A is a vector quantity, and B is a vector quantity, and E is a vector quantity, just list the letter. Right, so putting that in the Zoom chat for me. Right, which of these are vector quantities based on what we just spoke about just now? Let me just grab a bottle of water and come back. Right. So just to recap, vector quantities out of these three is going to be B and C. The length of a piece of wire is a scalar quantity, right? That's only capturing one dimension, the length. The force needed to move or lift up a shaft, we're talking about magnitude, the size of the force, and direction to move it up. A move from a door, from a door to your chair. Excuse. That's talking about displacement. A change in the position of an object from its initial point to a final point. You're moving from your door to your chair. So that is a vector quantity. Speed of a galloping horse is scalar because that's just telling us magnitude. It's not telling us direction. Distance is also scalar. That's just like length. You tell us the distance between the two tongues, but there's no direction involved there. All right. So our vector quantities is B and C. Everybody understand that now? You all okay with that? Just drop a 1 in the chat board if you are. Is that clearer? Yeah. Right.
So you could define scalar one more time, please.
Scalar, sure, no problem. So scalar quantities, they only have size, but no direction. So length, that's scalar. If I measure the length of this pen, all I could really measure is just the length of it. It doesn't tell me the direction. Mass, we say weight, but weight is incorrect. The correct word is mass, right? When we talk about weight, we have to talk about the force acting in a particular way, right? So it's not, we don't say the weight of, the correct thing scientifically or mathematically is the mass of an object. That tells you the amount of matter in the object. So if I have a phone, you know, you go on Amazon and they tell you the mass of the phone. It tells you the amount of ounces the phone would weigh, right? Only measuring one thing. There's no direction there. Temperature is another scalar quantity. It's just telling us how hot or cold something is. There's no direction involved. So scalar quantities, they only have magnitude or size, no direction at all. That's different from vector quantities because vector quantities capture both the size and direction. So a good example is force. The force of an object tells you how strong or weak a push or pull is, and it tells you the direction in which the force is going to be applied. If it's to the right, if it's to the left, it's going to be down, if it's going to be up, right? That's the example of a vector quantity. Is that clear now?
Yes, sir.
Yeah? All right, nice. Everybody okay with it, right? Difference between scalar and vector quantities. So we're moving on. Representation of vectors. So usually in mathematics, we represent vectors by line segments. So the length of the line usually tells us the magnitude of the vector and as well as the direction. The direction is really indicated by the arrow, right? So generally, vectors are denoted by a letter, usually common letters that are bold in type, right? Because of that, because we can't write a bold letter in our notebooks, we'd usually just write it with a little line underneath it, as they have shown here, right? Alternatively, if we have a start and ending point for the vector, so we call this array. So for example, if I have a and a B as my start and ending point, I know it's the start and ending point because of the direction of the arrow. This arrow is telling me we are going from A to B, right? So I would write it as A to B, like that. If we change the direction and we write the arrowhead this way, then this vector is now B to A. Although they may have the same magnitude or size, if the lengths of these are the same, they're different vectors because the direction is different, right? In that sense, the direction could be different. Opposite direction, same magnitude, right? Magnitude of a vector, the size of the vector. When we're talking about the magnitude of a vector, we usually write these straight line brackets outside of the vector. So this is asking, or this is saying the magnitude of A, right? And this will represent, or this is equivalent to the length of the line segment. So usually to do that, we would need some box paper or graph paper. And the magnitude of a vector is really just Pythagoras theorem, because you're looking at the horizontal displacement, looking at the movement to the left or right versus the movement up or down. So we would take this as is. If I have a vector A, this is the line on graph paper, I would need to count the number of blocks that I'm moving this way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then same thing this way. 1, 2, 3, 4, 5. So this is 12 this way, 5 this way. And that's what I tell you, it's just like Pythagoras theorem. And we have no subtracting or anything to do here. It's just the square of the two numbers and the square root of it, right? So 5 squared plus 12 squared, right? 25 plus 144, right? And that's the root of 169, which is 13 units, right? And that's how we find the magnitude of the vector. So usually when you're given a question to find the magnitude of the vector, you would have to either draw it on a graph page or they will give it to you on a box sheet like that. And usually assume that each square is 1 unit in length. Notice as well too, my unit of measurement, I say units. Sometimes when I work these out, like for example here, the root of 20, you put it to 3 significant figures. All right. So 4 squared plus 2 squared, that's going to be 16 plus 4 is 20. The root of 20, you get a long decimal number, you put it to 3 significant figures. Is everybody okay with that? Does that make sense to you? Easy? Let's try some. So I'm gonna do 1 here with you. Let's look at, I am gonna do H. H is the largest one. So remember when we're doing magnitude, we write it like that. Now I need to look at my movement. So I'm moving this way. So that's 1, 2, 3, right? And then up 1. Notice where I start counting from, right? 2, 3, 4, 5, 6. If you want, you could count the actual blocks. 1 block, 2 block, 3 block, 4 block, 5 block, 6 blocks. Right? So I'm gonna say here, addition is commutative, so it doesn't matter the order. If you put 3 squared plus 6 squared or 6 squared plus 3 squared, doesn't matter. 9 plus 36. Root of 45. I get back a scientific calculator. I don't know. Where my calculator go? 45 square roots. Again, 6.708203. We wanted the 3 significant figures. So the 3 significant figures, that's 6.7. Yeah? Everybody understand now? Just drop a Y in the chat. What if you do? Do one more example. Yeah, sure, no problem. Let's look at E. We want to find the magnitude of E. So to find the magnitude of E, you're just looking at the amount of blocks that we move in this way versus this way. Right? So let's check the blocks. So 1 block, 2 block. So that's 2 units that in that direction. And then if we do underneath here, 1 block, 2 block, 3 block, 4 blocks. That's 4 here. Right? So the magnitude of E is equal to the square root of 4 squared plus 2 squared. 4 squared is 16. 2 squared is 4. That's the square root of 20. The square root of 20, I think I saw that earlier on, is 4.47 units. You okay with that now? Everybody?
Yes, sir.
Yeah. Shaniqua, you good? Yeah, you good. Julia, good. Solana, you good there?
Yes, sir.
Right, excellent. So I'll leave in these two that I did on the screen. Right, and you're going to do the others for me. So you're going to do A, B, C, D, F, and G. Yeah? All right, guys. So here's the solutions to the questions you had on the screen there just now. All right. What we will notice is for the magnitude of A, B, C, and D, right? Although they're in different directions, right? Clearly, you can see that A is in a particular direction. So is B, D, C. The magnitudes are still the same, right? It's still a displacement of 2 by 1. And when we find the square root of that, right, that works out to be the square root of 5, which is the same 4.4. 2.24 units, right? The 3 significant figures. So vectors can have the same magnitude, but they could be in different directions. Everybody okay with that? Just drop a 1 in the chat. But if you can, if you're okay with it. This is our D, right? Now I'll do it over. So another way we could represent, or vectors can be represented, is using column matrices, right? It tells the same, or it paints the same picture as we just saw on the graphs. So not all the time you may see a question where they will write a graph and tell you, well, you know, this is the vector and you have to work out now the number of squares. Sometimes they would tell you that these are the vectors. Now remember, when writing vectors, we just put the line underneath them like this, right? So that you know it's a vector. Right. So just remember when we do any vectors like that, you know, they would either, if it's written, I'll have to put a line underneath it. In other cases, like in a textbook, they might just bold the letter. Now we could use the same things, right, to find the magnitude. Find magnitude of each. So I will do one. Right, so the magnitude of the vector A is equal to, same thing as we was doing before, 3 squared plus 4 squared right, 9 plus 16. Five units. All right. Everybody was okay with the others, right? Even this one, F, where it had a half of a block. Everybody was all right with that? Yeah. Yes, okay. Right. So for these, it's the same thing. It's just that in some instances, you might actually get a graphed page where you have to count the blocks. In other instances, they could use column vectors to represent the which is very more often than less. They would use the column vectors, and sometimes in a rare situation, you may have the actual graph where you have to count it out. But more often than less, we will use the column vectors to represent the vector. All right. So just quickly try these for me. Find the magnitude of B, C, and D. Right, and then we'll move on. Everybody okay with that? So on the screen, we have our solutions now for those three remaining questions, where we have the vector expressed as a column matrix, and we are asked to find the magnitude of each. So it's the same process, right? We use any two numbers. It doesn't matter which number you put first. Generally, I tend to take the top number first, but addition is commutative, so the order is irrelevant. All right. Is everybody able to get these answers? If you would just drop a Y in the chat board. Yeah. Good job, guys. All right, so we're moving on a bit. This one you'll do for me for homework. Right. I will send these. I'll send the entire PDF inside of the group chat, and I also have to create a Google. I have to send you the link to the Google Classroom where I'll be uploading this together with the recording for your future reference, right? So we just want to talk about some other vector properties that should kind of take us to the end of our session. I just have a few vector properties, and I just want to show you guys a bit of displacement vectors. So equal vectors, two vectors that have the same magnitude and are in the same direction are equal, right? So if we say vector A is equal to B, that means that the magnitude of A and B are the same and the directions as well would be the same, right? So they can't be going in opposite directions. And generally, vectors can be represented by any line segment of the right length and direction, regardless of the position. So even if they are far apart, close in, once they're in the same direction, right? And they are the same length as in the diagram here below. Where's my oh, here it is. Right, so all of these, they're all in the same direction. Look at where the arrow is pointing. And we can see that they're the same length. So they are called equal vectors, right? Negative vectors now, if two vectors have the same magnitude, but they're in opposite directions, then we could write them like this, right? So this is the same length as A. A is going from here to here, same magnitude, I mean, right? But B is in the opposite direction. So B is actually a negative. It's the same vector, but just in the opposite direction. So B is negative A, right? So negative A is a vector that has the same magnitude of this vector here, A, but is in the opposite direction of A. So we could say that A and B are equal and opposite. They're equal in terms of magnitude, but opposite in terms of direction. So for example, if we are using the head and tail method, where we're talking about the starting and ending point, right? A, B, and C, D, these two vectors here, use a different color. These two vectors here and here, right? They are equal because they're the same length and they're going in the same direction, right? So is this one too. These three, all same length, same direction. HG, however, same length but opposite direction, right? So AG, right, we could say is a negative AB. It's the same thing as negative AB. It has the same magnitude but opposite direction. Does that make sense to everybody?
Yes, sir.
Yeah, all right. Sometimes we could use a scalar. Scalar is like a multiple that we could put in front of a vector. So if we realize that vector is in the same direction but slightly larger than the other, we could use a number to represent it. So for example here, 2A is twice the magnitude of A. If we change the direction, then we just put a minus sign in front of it. So to change the direction of a vector, usually it's just the negative of the vector, right? That makes sense? Important concept because you'd use it a lot when we're looking at displacement vectors. Now, equivalent displacements or displacement vectors. And this is what you're going to see a lot of in your CSEC paper, right? The displacement from A to B, and when we use the word displacement, it's a movement from one point to another in a particular direction, right? That's why we use the word displacement and not movement. So if we are moving from A to B this way, right? Like that. Sorry for my proper foot, right? The movement of this vector could be described as AB with a little arrowhead telling you that it's starting from A and going to B. So we start from A to go to B, and then we go from B now to C. See the direction of the arrow? So this is denoted by BC. Now the movement of A, the other pen now, A to B, plus the movement of B to C gives us the result of going from A to C. It's like an alternative route. So, I don't know how much are you guys familiar with Shogunas, right? But if you're traveling from Shogunas, there's two things you could do. In Shogunas proper, you could take a highway taxi from KFC in Shogunas, and that goes down the highway into Port of Spain. It's a straight route. Alternative to that, you could take a green band maxi that is going to go along the southern main road to Curep. And then from Curep now, you can take a red band maxi from Curep Junction to City Gate. And that's going to achieve going to Port of Spain. So you can think of this area being as Shogunas by KFC. Right? And this is our route on the highway to go to Port of Spain here. An alternative to that, we could stay from Shogunas and go to Curep here, drop out of the maxi in Curep, and then take another maxi now to go down the bus route to Port of Spain. But ultimately, you are still going from Shogunas to Port of Spain. You follow what I'm saying? Does that make sense to you guys? That's what these resultant vectors or displacement vectors is about. Sometimes we may know the value of the vector AB, and we may know the value of the vector BC, but we don't know the value of the vector AC. But look at the arrows. The movement of A to C could be achieved or found if it is we add the vectors A to B and B to C. So it must go from A to B and then from B to C. Just like that analogy that I gave you guys with going from Shogunas to Curep. Think about the A as, not to Curep, to Port of Spain. The A as Shogunas, the C as Port of Spain. The common area in the middle here is Curep. So when I'm taking a long way down the southern main road, after travel from Shogunas to Curep Junction, then start again in Curep Junction in another taxi and go to Port of Spain. And that results, or the result of that is the same as going from Shogunas to Port of Spain. Does that make sense to you? Just drop a Y if it does.
Yes, sir.
Yeah, everybody? Yeah. Now the trick is, when you're doing this, the middle letters must always be the same. Always think about that example I give you with you're going from Shogunas to Curep. When you're reaching Curep, the green band maxi doesn't swing on to the bus route and go to Port of Spain. You have to come out the green band maxi and board another maxi in Curep. So your journey is going to start from Curep again before you go to Port of Spain. That's why these two middle letters here has to be the same all the time, right? Now, another key thing to look at is when you have this triangle, you look at the arrows. These arrows is going in a clockwise direction, going to B, then it's going to C. So this is the route here, A to B, B to C. This one is not following that exactly. It's actually going in the opposite direction and going straight from A to C. So the result of going straight from A to C is the same as going from A to B and then from B to C. And that's how we get this vector equation. Very, very important, right? Very important. So let's get a little bit of practice with that. So I want you to try writing some of these vector equations to me. The first one I did for you. Right? Now, what I did is I wrote the resultant vector with a red arrow so you could see it, right? So I want you to find, in each of them, I'll tell you which one I want you to find. Here we find in X to Y, this vector here, going from X to Y. And to do that, we're going to go from X to Z and then from Z to Y. See it? X to Z, Z to Y. Look at the arrows. It's following each other, it's leading on to each other. Yeah? Let me do one more. Here we want to find M to P. So I'm going to travel M to N and then start from N and go N to P. So I'll write it as M, N, and just like that example with QF, I have to start from here again and go to P. So the N letters is the resultant vector that you're trying to get. Look at that. That's the resultant vector that you're trying to get. And the middle letters always match. See that? Middle letters always match. Everybody understand that?
Yes, sir.
Yeah, easy.
Yes, sir.
All right, nice. So let me get you to try some now. I just need to make this a little smaller. Use the little markup I'll do there. All right. So that's you. That's you guys there. You're going to try this one. Right, so you're doing 2, 3, 4, 5, and 6. Yeah? So you're looking at the solutions for these. Now, a little trick that I used to use was I like to write the ending letters like this. And then I know the middle letter to match, which is the N. So this way, I never really get it incorrect. Right, so it's a little shortcut I used to do when I was just learning how to do the vectors. So I don't make any mistakes or confuse myself. So I write the outside and then I do the inside. See? Same thing here again. Outside. And then I'll do the inside because the letters on the inside is always the same. Now I kind of break this up in like little baby steps for you guys. You'll actually see it when it all comes together in a vector question. But this is one of the key things to be able to write the vector equation to then be able to work out the question. So it's important, right? Just one last thing before we go. I just want to look at the addition of the vectors, right? It's the same thing as you was doing, except that sometimes they will denote the vectors either by these little letters or they might use the column matrices that I showed you before, right? And we do some example with the column matrices as before. But it's the same thing, right? So X to Z, I denoted it here with a baby X or little x. And Z to Y, I denoted it with a Z. So X to Y is formed by adding X and Z, just as you was doing before, right? This X plus this Z, right? Same thing for here. M to P is going to be M, right? From M to N, N to P, right? So what you could do is you could write your vector equation, just like I showed you, wrong pen. M, P at the end, N in the middle, right? Mn is little m, Np is little n. And that's how you're going to get the vectors. Everybody get the hang of that? I'll do them with you. Same thing again. J, I write the outside, then I do the inside. JK is little j, and KL is little k. Right? Outside, inside. See how easy? DE is little d, and EF is little e. Right? Later on, we will add vector matrices to them so we could actually add real values. Outside, inside, little r plus little s. Outside, inside, little w plus little x. Yeah? Easy? Everybody okay with that now? All right, guys, so I'm gonna wrap up with that. As I mentioned in the other classes, I'm gonna download these, and between tonight and tomorrow, I'll be sending them out to all the groups. All the groups, and then we're using Google Classrooms as well. Google Classrooms, I'm gonna break it up into this. Each section is going to be based on a session. 5 vectors, part 1. Right, and in that section, you're going to have a link to your recording, a YouTube link. You're going to have the PDF, whiteboard, right? And PDF whiteboard, the link to recording, and really homework, right? I think you just have one set of homework here, and I might just add like a small quiz, nothing too much, right? But make sure and do it, because after mark those, like I was mentioning earlier, in your use that miss. Every month I'm going to provide the parents with a progress report that's going to give attendance and how you perform in your assessments, your weekly assessments. So more or less homework, not so much assessments, but something for us to keep track in terms of how you're progressing, and also for me to get an idea of your understanding if I might need to look over a topic, give individual assistance to somebody, make an extra video, right? That's to kind of give some feedback to me on this end, so that I can help improve the overall process, right? As it relates to each individual student. All right, guys. So I'm going to wrap up with that for today. Just want to thank you for coming out.